So after these tutorials, these are some sample questions that I've compiled for you to be able to try your hands on. This tutorial will give you a solid understanding of what you need to know in order to be able to kind of tackle questions about volume of fourth revolutions. So for this type of question that I compiled, I have around 18 questions, right? That for all of them, you have to be able to try your hands on after you watch the videos that I've posted on this YouTube channel, which is College Education Tutorial under volumes of revolution. So these are the questions, so you have to try your hands on them, sketch it, follow the same procedure that I'll show you in the video, try to understand the basic concepts and then come and apply them here. I also gave you some example in these YouTube tutorials that you can try your hands on. So it's like you learn and you work some examples. So you learn with examples, and at the end of the day you get some solid understanding in order to be able to use it wherever you find yourself. Yes, so these are the sample questions that you can try your hands on, and after that you'll be good to go. Yes, so when you are done to, the answers has been provided over here. So whatever you do, you get to know whether you are getting the correct answer or the wrong answer. But the advice that I'll give it to you is that mostly try your hands on the question first, try and solve everything to the end, and then come and verify whether you get a correct answer or you need to make some changes. I think in that case you'll be able to build up your neurons, you'll be able to kind of do some reconnection in your brain to kind of help you to establish the basic understanding. I will also upload this file under the description section of the video of my YouTube channel so that you can have access to it. Now let's go straight to today's tutorials. So now, what if we are not revolving above the x-axis or the y-axis, or let's say x equal to 0 or y equal to 0? What if we are not doing that, but rather we are revolving around a line that is, for example, y equal to 4, as you can see on the screen? How do we go about that? So let's quickly look at it. So now the question is, determine the volume of solid obtained by rotating the region bounded by y equal to x squared minus 2x and y equal to x about the line y equal to what? 4. That is, now we are not doing it at y equal to 0, which is the x-axis. Now we are doing it at y equal to 4. So how do we do that? So let's quickly try and see how we can solve it. So as we did in our previous example, the first thing that you have to note here is that, first of all, you have to plot the functions. And how do we plot the function? The quickest way to help you to plot this or hand sketch this function is to kind of find the meeting points of the two functions that you are sketching. So in that case, these are my two functions, which is what? Y equal to, and put it here, y equal to x power 3 minus 2x, right? And then y equal to x. So how can we know that this function is meeting at this particular point? So what we do is to equate the two functions. That is x power 3 minus 2x equal to x, right? So when we equate the two functions, we can bring all the x values to the other side, right? We can bring all the x values to the other side to help us simplify things. So now we can do something like, okay, x to the power 3, right, minus 2x minus x, which is equal to 0. And in this case, we'll be able to simplify it, and that is x power 3 minus 3x, that is equal to 0. So how do we find the values of x, right? So this is how you can find it. You can factorize the common ones out. Here we can see that the common variable here is 3x, right? The common variable here is x. So we just factorize the common variable out. So when you factorize the common variable out, now we have what? X squared, right? Minus what? No, it's not y power 3, it's y power 2. Excuse me. Yes. The function here is y power x power 2. X power 2. So you can just correct that. Yes. So x power 2. So because it's x power 2, then it makes our work even simpler. So what we can do here is kind of, let me put it back. Okay, kind of get x power 2 minus 3x equal to 0. Now we can see that we will have something like x out, x minus 3, which is equal to 0, and therefore we have what? Don't forget that here you have to correct as well. So we have what? X equal to 0, and then x equal to what? 3. So now we know that these are the meeting points for these two functions. And now the next thing is to try and sketch these functions, right? So let's quickly do the sketching. Okay, let's say we are sketching it here. Let me go here. Let me draw it here. Okay, so now I have my x value and my y value. Let me even put it here because the function we are revolving it around y equal to 4. Because we are revolving around y equal to 4, let's kind of make x bar come a little bit down so that we can kind of have a lot of space up there. So based on this, we have our y and we have what, our x over here. And now let's plot the function one after the other. We know that we have y equal to x squared minus 2x. So you consider this a quadratic function. So since it's a quadratic function, how do we go about this? So we find the turning point. So now we know that our turning point will be the first derivative should be equal to 0, right? That is we can see this, we can automatically see that this graph is what should be a minimum graph if we are to draw the full one, right? So in that case, we are going to get something like, okay, 2x, which is the differential, right? The differential of this function, that's dy dx. This function 2x minus 2 should be equal to 0, right? So in that case, we are going to get 2x equal to 2 and then x equal to what, 1, right? So if x equal to 1, that means that what will be our y value? When I put my y value here, I'm going my value for x here, we are going to get y equal to x squared, that is 1 squared minus what, 2 1, and that gives us a negative 1. That means that if we have a negative 1 here and then we have 1 here, that means here will be our turning point, right? But we know that the graph passes through 0, so we can sketch it like this. Let me put it here, right? So that be our turning point. Is that okay? There's no need for us to find intercept because actually we are kind of trying to do a hand sketch of this, and the only important thing that we need is to know the meeting points, right? And then we know that the next one, it will be meeting at 3. So let's say x is 3, right? Mean that x equals to 3, but let's look at the y value as well. We can put this one in any of them. When I put 0 here, I'll still get 0. But when I put 3 here, I'll get 3. And when I put 3 here too, I'll get 3 as well. So in that case, because 3 square will give us 9 minus 2 times 3 6, so we are going to get 3. That means our y value for here is also going to be 3, right? So in that case, we know that it will be meeting here something like this. So here is 3, right? And then let's see, I don't want it to go up a little bit. Okay, let me clean this a bit down. Let's say our 3 is here. Let's say our 3 is here, right? Yes. So this is what we have. And then let's look at our next one. So we have been able to plot this, and we are going to look at y equal to x. Since we are doing y equal to x, we know that this is what, a positive, it has a positive gradient, and since it has a positive gradient and it's a line, that means that it will have the nature of this, and we know that it's also passing through 0 and it's meeting this graph as well, 3 as well. So in that case, it's passing through 0 as well and meeting this graph at this point, right? Exactly. So let me put this one here. So this is for those of us who don't use graphing calculator, right? This is how you can plot it, right? So now we have this one, we know the meeting point, and we have something like this. And let's assume that our 4 is here. That means our y equal to 4. Our y equal to 4 will pass here. Is that okay? Our y equal to 4 will pass here. Is that okay? So there's 4. Right, and then 4. So now, because we have this, now we have to do our volume revolution. And don't forget that this figure, when we turn it, we do the volume of revolution. When you do the volume of revolution, it will be symmetrical about the axis of rotation or axis of revolution. And the next figure will appear. So when we have to do this, you are going to get something like this. Not on scale though, but you have to something like this. And then how do I put it in a correct form? Let me put it that way. And then so actually it's supposed to be let me put it this way. Yes, so now I think I'll have the actual thing. Yes, So this one and this one is supposed to be at the same line. This one and this one is supposed to be at the same line, right? So let's see, yeah. So you can see this is a 3D of how it was revolved, right? So now let's quickly look at our sketch here. This is what we have. So how do we find the volume of revolution? So now this is our figure. This will become our whole figure. Everything is our figure. If we are showing the 3D, as you can see over there, that's our figure, right? So the next thing that we have to do is to be able to figure out our outer function, the radius of our outer function, the radius of our inner function, right? So how do we do that? This is a bit different from the one that we did earlier on, because the one that we did, we were revolving it around either the y or the x axis. Things were easier for us, right? So now for this part, how do we figure out the radius? The radius is from the function to the axis of rotation at any point in time, from the function to the axis of rotation at any point in time, or from the function to the axis of rotation at any point in time. That will be your radius. So based on that, at any point in the function, you can see that the function is changing. So at this point, the function value will be 0. At this point, when I trace at this point of the graph or the curve, when I trace to this side, you can see the function value will be changing. At this point of the curve too, when I trace it to the y value, you can see the function value is also changing. So you can see that the function is the one which is changing. Is that okay? That means that if I want the distance from here up to this graph, this is what I can do. I know that from the x-axis, that is 0 to this point is 4. So if I want the distance from here to here, of which I can estimate it as my radius, I need to find the distance from here to here, right? Yeah, and that will be approximated by the function for me. When I get it, I know that from here to here is 4, so I have to subtract it from the 4, and I'll get the estimated distance from here to this point. That is a simple thing that you can do, right? Simple thing that you can do. So because of that, we can form the radius expression, and in forming the radius expression, you can do same for this. You can do same for, or you can do it from any side, from here to here or from here to here, at any side of the function. Because at any point of the function, the graph is actually changing and the 4 is constant, then we can form the radius expression as, for example, let's take the outer function for instance. The outer function will have a radius of, now the 4 is not changing at any point, because at this point, I'll have to calculate the distance here and subtract from the 4, and then I'll get the distance here, right? So at this point, I'll have to calculate the distance here, right, with the help of the function, and then subtract from the 4, and then get the distance from here to here. That will be my radius. Is that okay? That's how it will be. That is from this one. For the outer function too, the same thing applies, right? If it's here, you have to be able to calculate the distance from here to here, and then subtract from the 4, and then you'll be able to get the distance. And because here the value of y will be what? Negative. When I do 4 minus that value of y, it will give me plus. That gives us the actual distance from where this function is to that of this one. That means we are adding something small from the x-axis, which is our reference, to that of the 4, from 0 to 4, right? So in that case, we'll be able to estimate it. So based on that observation that we are seeing over here, we can say that, okay, we have the constant, which is 4, which is not changing, and then the function, which is what? Where is the function? So if we are looking at the outer function, what's the outer function? The outer function is what? X squared minus 2x, right? Let me clean this. And then we can simplify it to get what? 4 minus x squared plus what? 2x. And that gives what? 2x, let's say minus x squared plus 4, or let's say 4 plus 2x minus x squared. That will be your what? Your outer radius. So now let's look at our inner radius. Our inner radius can be represented as R. The same approach. You pick the constant which is not changing, and then we subtract the inner function from it, which is what? X. So now our inner function will have something like this as our radius, right? So in that case, the same approach as we did for our previous example, what we can do is to find the area. The area of the outer function is going to be equal to pi capital R squared, and that gives us what? Pi. We know that the radius is what? 4 minus 4 plus 2x minus x squared. And in that case, you can go ahead and say, okay, 4 plus 2x minus what? X squared. And don't forget that's all squared, right? And then the a in are going to be pi, and then the radius is 4 minus x all squared. So to make the work simple for us, let's quickly try and simplify things before we subtract them. So let's say our volume of evolution is equal to integral of, now we know that our limit of integration per the analysis that we did for the x y equal to 4, right? Because y equal to 4 is parallel to the x-axis, so we pick the values there from 0 to 3. 0 to 3, right? And then area out minus area in. And don't forget that the function is in terms of x, so we can do the x as well. So let's simplify it to make the integration simple for us. So now we can, for this one, for the first part, 4 plus 2x minus s squared out here, and another 4 plus 2x minus s squared. Of course, when you have a calculator, you can quickly do this. So this one all multiplied by pi for the a naught, right? A naught. And then for the a in, same thing, 4 minus x, and then 4 minus x. So that gives us 16 minus 4x minus 4x plus x squared, and that gives us what? That gives us 16 and then minus 8x and then plus x squared. And don't forget that the a in is also multiplied by pi. So when we go and subtract the a out minus the a in, so based on this is what we are going to get. That is the volume. After expanding everything, we are going to get the volume to be integral of 0 to 3 of x power 4, and then minus 4x power 3, and then don't forget here is minus 5x power 2, and then plus 24x. So this is what we have, and then all of them, don't forget that we have pi here, all of them with respect to the x. So the same approach we get from 0 to 3. Now let's start the integration straight away. So the integration straight away is going to be v equal to pi out x power 5 over 5 minus 4 x power 4 over 4 minus 5 x power 2 or 3 over 3 plus 24 x power 2 over 2, and the limit of integration from 0 to 3, right? So in this case, we can go ahead and kind of simplify things. So now we are going to get v equal to x power 5, v equal to x power 5 over 5, and then minus, you know, it's x power 4 over 4, so we are going to get x power 4 here, and then the next one is going to give us minus 5 x power what? Because when you look at this one, power 3 over 3, power 3 over 3, and then plus, now 24 divided by 2 give us what? 12 x power 2, right? So now this is what we have, and then all multiplied by pi, and then the limit of integration from 0 to 3. So we just put because everything here for the 0 part give us 0, we just have to put things in place. For example, 3 to the power 5 over 5 out here minus 3 to the power 4 minus 5 over 3, and then we get 3 to the power 3 plus 12, and then we get 3 to the power 2. Because the 0 part is giving us 0, we don't have to worry about that. We multiply by pi, and in that case we are going to get 153 pi over 5, and in decimal we are going to get 96.133. 96 point in decimal, we're going to get 96.133 as our volume. So basically this is not difficult. I have one trial question for you. So for this one, You have to try this question. It's a trial question that I have for you. But let me give some small explanation to this question. So determine the value of the solid obtained by rotating the region bounded by y equal to 2 square root of x minus 1. So they say rotating the region bounded by, so and y equal to x minus what? 1 above what? The line x equal to -1. You know the previous question we did rotated from y above the line y equal to 4, but here we are doing it on the x equal to -1 instead, right? So please quickly try your hands on this, and then you are supposed to get an answer as 60.3185. This is the answer, which is approximated as approximately 96 pi on 5. So this is the final answer that you're supposed to get for this particular question. So don't forget that if you have any question, just go to my comment section and then ask. If you need further clarification, I'll be happy to help you out. Thank you, and don't forget that you are watching College Education Tutorials, right? Your knowledge center where complex topics in engineering and mathematics are simplified. My name is Noah Adasi, and this is where we are ending this tutorial today. Thank you.